Yeah, no worries. Let's resume recording so that we can chat about some stuff. Yes, so it's been kind of a crazy week. So my house has sold. We've put an offer in on a house in Kelowna. It's been stressful and lots of things. So I was actually just on the phone with like the moving company trying to get that all sorted out. I was hoping that my classes this weekend were going to get canceled. I had line training this weekend, WSET part 2. So that happened this weekend. That was like 9 to 5. So, by the time I drive back from Kelowna, I was exhausted. So basically what I'm saying is not a lot has gotten done on my end other than me existing and trying to get life things in order. So I'm a little behind the ball on some of this stuff. So let's answer Colin's question. Is there a quiz this week? What do you guys want? Do you guys want me to draft up a couple of questions on partial fraction decomposition and post them as a quiz? Or are you happy for me to add the portion that would be this week to the quiz next week? So I can basically draft up the same questions. We'll just push that back a week and have the quiz next week. That'll give you guys a little bit of buffer time to start working on the assignment if you want. But I'm happy either way. You guys just let, if it's one of those kind of midterm weeks and you'd rather have a little bit of free time to not think about calculus, I'm happy rolling that way. Will the total amount of quizzes be the same at the end of the year? I'm not sure exactly what that means. I would prefer
if you did if you didn't do a quiz, would there be one less quiz for the year? Or it's kind of hard to explain. If we did,
yeah, like if we skipped one, then it would still be the same overall percentage that are allocated to the quizzes. So,
but would there be the same amount at the end? If there's 8 quizzes, would there be 7 now?
Yes, yeah, exactly. I'm not going to like shove 2 quizzes into 1 week, basically.
Okay, then I would like a quiz this week.
Nope, that's perfect. Okay, so a couple of people are saying let's do a quiz. So what I'm going to do this week then is I will make that quiz. I'll try to make that by the end of the day today and post it by tonight. And what I'll do is I'll put the due date, usually they're on Fridays, but I'll extend that due date to Sunday at midnight. So if you have the time to do the quiz this week and get it done before Friday, you'll be able to do that. But because I know I've posted it a little bit late, I'll extend that due date by a couple of days in case you need that little bit of buffer time. Okay, guys? So yeah, we'll roll with the quiz this week. It's already in my planner to do that. And then we'll have that due date by Sunday this week at midnight instead. Okay? So yeah, other than me not having that quiz ready, the assignment should be up and rolling. So when is that assignment due? When's the due date on the assignment? Do you guys remember? '21st. Okay, so you got lots of time on that. Still a little ways away. Beautiful. So what is that? That's like 2 weeks away. Golden. Okay, so there's not really anything else. I don't think there's anything else for us to worry about. I'll get the quiz up. There will be a quiz. And yeah, we're starting to move into some of the more intense topics, I would say, for the second part of calculus. So let's do maybe a quick review question here on partial fraction decomposition. And then we will start working into a section called sequences and series. This is really, I would say, the last major topic is sequences and series. And I want to talk a little bit about sequences again. So just kind of refreshing our memory on what those are and how to work with those kinds of things. Are there any other pressing questions, things that I need to have on my radar for you guys before we start this example? Thank you for the congratulations, by the way, Kate. It's very stressful. Did I end up posting practice homework? Yes. Where did I post that? Let me show you. I think I posted it under the course outline section. I think. Yep. So I put so under the course outline section on Moodle, there's a practice questions thing here. So yeah, you can go through those practice questions and find stuff that works inside the sections that you think you need a little bit more practice with. Okay, so I will just share that Word document with you. So this should cover all of the chapters from the textbook that we're going to cover this semester. So you'll be able to do most of this work already. We're about to start into chapter 11. This is going to be the last chapter that we cover. But you should be able to do most of the rest of this stuff. There might be a couple sections from chapter 5 you won't be able to do quite yet because we haven't talked about the summation notation and how to talk about where the definition of integration came from. So there's, I think, a couple early chapters that you might want to skip, but most of these later chapters, you can pretty much cover any of this stuff. So we've done all the techniques. We've done quite a few applications as well. So I think anything from kind of this big chunk you should be able to do as practice. All right. So yes, so one thing I've been able to do is get you guys practice homework. So, but there's still like what 3 other things I need to get done for. All right. So let's go ahead. Let's work on this question. This is a little quick review of partial fraction decomposition. Oh, I see what we want to do here. So to start this question off, let's do an integration by part. Sorry, I should follow Nathan's question up. So hopefully that works, Nathan, and you're happy with that. Any other pressing questions that need to be on my radar? Okay, not seeing anything popping up into the chat. Let's go ahead and let's work away at this particular question. So this is an awkward one because it's a logarithm. I can't really do a substitution. So the next best technique is to try integration by parts. And for integration by parts, we need a u and we need a dv. It's hard to integrate a logarithm that actually has something else within that function. So if I took ln of x squared minus x plus 2 as the dv, that would be a hard thing to do. So what we're going to do is we're instead going to take the logarithm portion as the thing we're going to take the derivative of, because it's relatively straightforward to take the derivative of a logarithmic thing. And then the leftover dx is what we're going to take as dv. Okay, that's how we're going to start off the integration by parts. So let's go ahead, let's find the derivative with respect to x here. And be careful, we're going to have to use the chain rule. So the derivative of this is x squared minus x plus 2. And then we need to take the derivative of this denominator to get 2x minus 1. Okay. So the du piece that I need when applying integration by parts is going to be this fraction times dx. Okay, working with the right-hand side, we can divide both sides by dx to get 1. And then integrating both sides, we get v is equal to x. Okay, and of course here we don't need to add a constant of integration. Integration by parts just requires that we take an antiderivative. So we'll just take the easiest one. And if you have access to your formula sheet, I always recommend having some of your formulas close by. What do we need? We need uv minus integral v du. Okay, so that's the formula we're going to use here when we apply our integration by parts. So u times v, so we get x times logarithm x squared minus x plus 2. So there's u times v. And then we're going to subtract off the integral of v times du. So x times this fraction times dx. All right, v du. That seems okay. I think we can make this work. Okay, I'm going to go ahead now and I'm going to expand through the numerator. Because what I've noticed is that the highest power in the denominator is x squared. And the highest power in the numerator is also going to be x squared. So it's going to be hard for us to do a u substitution here. U sub probably won't work. So I'm going to probably have to go through the long division procedure, see what pops out on the other side, and then maybe work on a partial fraction decomposition. So I think I'm going to be stuck having to do par frac, unfortunately. Have you guys done the lab yet using the par frac command on Maple? Out of curiosity, you can let me know in the chat if you've done that. Oh, someone has a hard no in the haven't yet. Okay, no, not yet. So you will eventually learn how to utilize Maple to do partial fraction decomposition. So make sure you attend that lab and take notes, because Maple is a very lovely tool for you to be able to double check some stuff. All righty. So that is expanding out. We get 2x squared minus x inside that numerator. I'm going to go through the long division procedure next to try to clean up that numerator. So I can't really do partial fractions unless the degree of the numerator is smaller than the degree of the denominator. So we're going to be forced to do long division, I think. Okay, so we are going to take 2x squared minus x, and I'm going to add a placeholder of 0 here as well. And we need to divide that by x squared minus x plus 2. Okay, luckily this long division isn't going to be too tough. We just need to multiply our leading term by 2. That's going to give us 2x squared minus 2x plus 4. All right, and let's do a subtraction. So 2 minus 2 is 0, negative 1 minus negative 2. So we have negative 1 plus 2. That's going to give us an x. And then 0 take away 4. Okay, so that's the long division procedure. See if you can rewrite that integral out based on what we have here. So what's that new integral going to look like? So what's going to go in here? Okay, so I think what the long division procedure is telling us is we're going to have 2 wholes. Okay, and then I want to add the remainder portion. The remaining portion is going to be x minus 4 over x squared minus x plus 2. Okay, so that's what our new integration is going to look like. And then I'm, again, just going to try to keep cleaning this integrand up a little bit. I'm going to try to distribute and break this apart into 2 integrals, because the integral of 2, we should be able to tackle that one pretty quickly. And then we can maybe make a game plan for this second one. So we're going to have a subtraction of the integral of 2 and a subtraction of the integral of this other fraction. Okay, let's go ahead. Let's integrate this middle term. This n term is going to be another one of those funky examples where we might have to get a little bit creative. Now let's take a look at what a U substitution would look like, and hopefully that'll kind of guide us to what we want to do here. So if we go to do a U substitution, we are going to take the denominator of this fraction, which would be x squared minus x plus 2. Now, when we go to take the derivative and kind of move around our differentials, we're going to get 2x minus 1. Okay, so we've seen that already. We saw that up top. So in other words, if I could somehow get the numerator of my fraction to look like 2x minus 1, that would be a helpful thing. Now, it's the 2 that's going to be a little bit bothersome, but I mean, we can multiply and divide by 2. That should be fine. So I'm going to start making some slight alterations to this integral to make it work. Okay, so I need to get 2x. So let's multiply by 2 first. Okay, so I'm going to go 2x minus 8. Okay, so I've multiplied by 2 here. And I'm going to balance that by also dividing by 2. Okay, so in other words, I need to introduce the 2x. I do that by multiplying both the x and the -4 by 2. But if I multiply by 2, I'd change the question. So I also need to balance that by dividing by 2. So that's what I've done here to start. Okay, and then what I need to get next is I need to get a -1. So right now I have -8. So we're going to break up -8 into -1, -7. Okay, so we're going to get something that looks like this. We're going to have 1/2 integral 2x minus 1. So that's the thing that I need in order to make a substitution work. But we had -8 to start. So the -8, we're going to write that as -1, take away 7 more. And then what we're going to do is we're going to keep this part all together. Okay, so we're going to keep all of the bits that I need in order to make the substitution work. We're going to keep that together. Oops, sorry, not the dx quite yet. And then I'm going to subtract off that leftover stuff. So there's that leftover 7. I'm going to write out a separate fraction and deal with that over here. Okay, so like I said, I'm keeping all of the stuff I need in order to make a substitution work. This is essentially how we get rid of the x bit of this fraction. And then you're going to have a leftover numerical portion. We're going to have to deal, I think, with arctan in order to make this numerical portion work. Okay, so let's kind of just break this up into 2 integrals. We should have 1/2 integral of the thing we're going to perform a substitution on. Okay, and I'm going to factor out this 7. So we get -7/2 integral of 1 over our denominator. Okay, so that's how we deal with this problem. So the problem we had was up here. I'm going to highlight it in blue. This is a problem integral because it has an x and a constant number in it. So what we do is we set up a substitution to deal with the x portion. And then the leftover portion, which is down here, this 1 over x squared minus x plus 2, the leftover portion is going to become an arctan kind of integral. So these are, I would say, really common strategies to use after you've kind of gone into your partial fraction. Actually, we didn't even have to do partial fraction decomposition, did we? That's interesting. We tackled this whole thing without having to do parfrac. That's fun. I guess we could have done parfrac to make it easy. Does this factor? Is that a factorable polynomial? X squared minus x plus 2. 2, negative 2 plus 1. This does factor. So we could have made our lives maybe a little bit easier doing partial fractions. So I can maybe show you what that looks like after. Okay, so I just brought all of this stuff down here, and this is now the question we're working on right here. Someone remind me when we're done with this nonsense, let's go back and actually do the parfrac decomposition too, because it might be easier to do the parfrac if this original thing actually factored. Okay, so we're pretty much set up to do a good substitution here. Let's get that substitution rolling. Okay, so the whole point of doing all of that work that we did in the middle was to make sure that this substitution will work. Okay, performing that substitution, we get something that looks kind of nasty like this. Actually, no, it's going to be nice. It's going to be 1 over u. That's nice. That's a logarithm. All right, over here. Gross. We could try to complete the square. That's probably the best bet here. Will that work? Yeah, or we can also break that. We can do parfrac here too. We could also try to break this up to make this a little bit easier to deal with using partial fraction decomp. So it really kind of depends what you want to do. So, I mean, we could try to complete the square and make this into an arctan kind of problem, or we could try partial fraction decomposition, which potentially could be easier, resulting in a couple of logarithms rather than an arctan. So I'll let you think about what you would like to see. Do you want a bit more practice setting up an arctan kind of integration, or do you want a bit more practice with setting up partial fraction decomposition? You just let me know. I'm going to go ahead. I'm going to just simplify this middle integral. So someone says arctan. Oops, this has become long. U. Everyone else okay? Maybe trying to set this up? We can try and see if it works. So let's try to set this up with regards to arctan and see if we can get it to work, because this is a common strategy that you can use if you need to. Because there's 3 terms, in order to utilize arctan to do work, we need to complete the square. If I had only 2 terms, like an x squared plus something, it'd be much easier to utilize arctan. When you have 3 terms in the denominator, it's actually quite tricky. So we start by completing the square. So in other words, what do I want? I want to hopefully get I really want to get this, right? I need to get something squared plus 1 is kind of the end goal. But I really need something squared plus a number. As long as I get something squared plus a number, there's hope that we can make this work. So let's see. Definitely an x, right? So since there's no coefficient in front of my x squared, it's going to just be a singular x. I want to have a minus in here. And then I think we take, what do? We take the number, we divide it in half, and then we square it. I think that's the pattern, right? So I think we're going to have to add and subtract quarter. So I think 1/2 is going to work here inside the brackets. And I'm just kind of playing around and kind of taking some guesses. So let's see if I expand this out. So plus 7/4. Okay, so Damien is saying hopefully we should get 7/4 over here. So let's take a peek. Let's expand this out and see if we get x squared minus x plus 2. So I need to get x squared. I get this times 2, so 1/2. Yeah, so that gives me the x. And then multiplying this together gives me plus a quarter. And if I add 7/4 to that, do I get 2, right? Is this equal to 2? Yeah, this is 8/4, which is 2. Okay, so I'm happy with that. So with a little bit of play, we can complete the square. And this is what we get. So I'm going to write that down here. So we have 1 over x minus 1/2 squared plus 7/4. Okay, so there's our completing the square step. Now, the next step to make this into an arctan kind of thing is to make this number, this 7/4, has to be the number 1. So if you go to complete the square and you get like a subtraction down here, you're kind of stuck. You're not going to be able to use arctan at all. But because we got plus 7/4, I can now factor this 7/4 out and get the plus 1 that I need in order to make this an arctan kind of integration. Okay, so I'm gonna kind of ignore the other bits right now and just kind of zoom in on this last integral. Why is it x? Oh, sorry, this should be x minus 1/2. Yes, thank you. So let's go ahead, let's factor out that 7/4. Okay, so I'm factoring out 7/4 from the denominator. It's going to give us 1. And we're going to get x minus 1/2 squared over 7/4 plus 1. Okay, so this is factoring out that 7/4 in the denominator. This is going to let us hopefully clean up some stuff. So I'm going to try to clean up some of these coefficients. And I want to also clean up this in here a little bit too. That doesn't look super pleasant to me. So let's work on this outside part first. We can definitely get rid of a factor of 2. And then we have 7 divided by 7/2, which is 7 times 2 over 7. So all of this is actually going to simplify to the number 2, which is interesting. And then what I want to do inside of here is I want to get something squared divided by something squared. So I can kind of smush all of this together using my exponent laws. So we're going to be doing something that looks like this. I already have the thing squared in the numerator. And what I want to do is I want to make the denominator something squared as well. And the easiest way to do that is to take the square root of the numbers that we're working with. So for instance, if I take the square root of 4, I get 2. So that when I actually distribute this squared sign through the brackets, I would get 4 back in return. The only bummer thing is we're going to get root 7 in the numerator. So hopefully you agree with me that 7/4 is the same thing as root 7 over 2, everything squared. So it's this step I find, completing the square, at least you've had some practice with. This step I find kind of awkward because we don't usually think this way when we're trying to combine stuff like this. But that's going to allow us to make one big thing squared here. And that big thing squared is x minus 1/2 divided by root 7 over 2. Okay, I'm just going to pause there, let you kind of get caught up, and make sure that you're happy with the algebra, because right, like a lot of the trouble with arctan integration is just setting the algebra up properly. It's a real pain in the arse. And then again, maybe just over on the side here in red, I'm just going to take this expression. So we have x minus a half. And we're dividing by root 7 over 2. And I'm just going to try to simplify this. I'm just trying to simplify what's inside the brackets a little bit. Okay, so I'm going to, instead of dividing by root 7 over 2, let's think about it as a multiplication by 2 over root 7. And when we distribute through the brackets, we should get 2 over root 7 times x minus 1 over root 7. Okay, so essentially we get 2x minus 1 over root 7. Okay, so that is the setup for creating our arctan integration. In order to actually do the integration, we're going to perform a u substitution to get rid of the 2x minus 1 over root 7 and replace that essentially with the letter u. So let's go ahead, let's set up that u substitution. We're going to take everything that's inside the brackets here. And then when we take the derivative and multiply by dx to both sides, we should get 2 over root 7 dx. In other words, if I wanted to, I could replace dx with root 7 over 2 times du. All right, so let's go ahead. Let's perform that substitution. We will get 2 integral 1 over u squared plus 1. And then dx we're going to replace with root 7 over 2 du. Interesting. The 7s are going to cancel here, or sorry, the 2s will cancel. And then we're going to get root 7 arctan of u. Okay, we know what u looks like. It's 2x minus 1 over root 7. Okay, so what we're looking for here is arctan of 2x minus 1 over root 7. We're going to add our constant of integration. I'm just going to kind of zoom out a little bit, and we're going to start bringing down some of those other terms that we left way up top here. Okay, so final answer should look something like this. X ln x squared minus x plus 2 minus 2x. Ooh, this is intense. Okay, plus some stuff. There, so there's our full final answer. That looks gross. That looks like that was painful. That's hard. These are hard questions because, well, the way that I had set it up was set it up as a substitution plus an arctan integration. I find those just to be quite challenging styles of questions, personally. It was quite the integral. I'm curious to see what, so while you guys are finishing that up, I'm just curious to see what the integral calculator would have told us to do. I always like to kind of double check stuff with the integral calculator, right? If I'm like, especially when doing these partial fraction kinds of things, they can be a real pain in the butt to do. So yeah, once you start to learn some commands in Maple to help you, that's really beneficial as well, because Maple will kind of be able to solve some of these partial fraction decompositions easier for you. So yeah, I mean, it looks reasonable. I mean, it looks like it's a thing that we got. I mean, if I flash the integral calculator up, you can kind of see that it looks very similar to what we got, right? It has the root 7 arctan of stuff. It has the 2x here. It has the ln of x squared minus x plus 2. All it's done is it's found a, so this is the common denominator form. I guess if we kind of scroll back up here, this is what we're looking for. I think that's roughly what we got, right? Hopefully. I think that's what we got. Yeah, x times stuff minus this. They just got rid of the absolute value signs, which is fine because that must be a parabola maybe that lies above the x-axis. No, I don't know. That's weird. Minus x plus 2. Cool. So I'm happy with that. If you're happy with that, we could, does this factor though? Does this really factor? This must factor. Because now I'm curious. Now I'm really curious to know if it's worthwhile to do partial fraction decomposition, right? Like, I'm kind of curious now. So it shouldn't factor. That's weird. Why am I thinking about this incorrectly? So I'm thinking that minus 2 plus 1, oh, it's not going to work because the plus 2 is positive. So we can't do partial fraction decomposition because this is an irreducible quadratic. So I was thinking that I could factor this, but it's actually not factorable. So the way that we have tackled this question is the only way to do it. There's no other way because I can't factor this. So I can't make, so if I kind of go back to the example here and just kind of flash that example up for you. If I go back to, I was wondering like up here, after we did long division, if we could use partial fraction decomposition up here. We could only do that if the denominator was factorable. Our denominator was not factorable. So the way that we've done this integration is the only way to do it. So setting up a substitution and setting up an arctan integration. We had to do that. Cool. How's your brain doing? I feel like my brain like literally just turned to mush. hold up for a minute. I need to go get a new brain. Okay, I very easily could have missed a minus sign. Do you know where that minus? Yeah, I lost my brain last term. Yeah, exactly. This term is a little, I find this like a more exciting term. Like I really like integration a lot. I like the puzzle aspect of it. But yeah, it's definitely do you know where we might have missed that minus sign, Kieran?
I think it may have been when you first split up the integral with the 1/2 factor before it, but I'm not sure. It could have just been me looking at it wrong.
Oh, up here.
I think you may have only put the negative sign into one of the two instead of both.
Oh, I see. Yeah, you're right. It looks like I missed. Or no, that seems like this seems okay. So let me check my signs and maybe we can kind of figure out where that got lost. So we need a positive one of these, which we have. We need a minus 2x, which they have. We need a positive 1/2 logarithm. Oh, okay, that's where the error is. So the error is here. So where did that come from? That came from our substitution, which we did way back here. And so I think what happened is I forgot to carry this minus sign down, right? I think I forgot to carry this down here, right? think that's the error. Is there also an error in our arctan? So do they have an opposite sign for the arctan as well? Should be a -7. Nope, they have a plus sign. So that one came out okay. So yeah, I think it's probably just an error here. So it's probably this bit, right? These should be minus signs. I think that'll solve the problem for us. So yeah, I'll zoom out so you can kind of see where those highlights are. So it looks like I missed a couple of minus signs. So you might just want to alter them to be minus signs. Thankfully, that's all it was. Sometimes you can differ by like a number, and trying to find the number is really hard. But thanks for bringing that up, Kieran, because I do think this highlights an interesting way to check stuff. So when I was a student, I would always kind of verify with either Maple or with the integral calculator. And so if you notice that you differ by a sign like this, each one of the chunks of your answer comes from something up above, right? So when I look at this final answer, this chunk came from the original part, which was the integration by parts. If there was an error in this, I should go all the way back up to where I did the integration by parts and check to make sure that I did that correctly. You know, where did this come from? This came from the integral of 2, right? So if there was an error here, I'd go back up and look and see, and look around where I made the integral for 2. Where did this factor come from? This factor is our substitution factor when we did our U sub. So go back through your U sub steps and see if you can find where that mistake is. And of course, this is our arctan boy. So you can kind of chunk up your final answer into like different pieces that we worked on. And if you have made an error in either the sign or like a constant number, but everything else looks the same, just kind of go back and glide your way through some of those steps and see if you can find where that error is. So hopefully that gives you at least an idea of how I might kind of double check answers. And I totally missed that minus sign, so thank you. Yeah, this is smooth brain right now, like smooth zero brain. Okay, that's all I want to cover for partial fractions and other techniques. So we didn't really actually do a partial fraction decomp, did we? We did more of setting up a long division, setting up a substitution, and setting up an arctan, which I think is good. It's good to have those tools, I think, in your tool belt. Question, let's see, do I have the formula sheet for the final exam? I do. Okay, I want to look at something on the formula sheet with you guys before we start sequences, because I think something interesting might be on the formula sheet for you guys. Here it is on the formula sheet, which you can find under the exam section. So if you go click the final exam, it'll have some practice exams in the formula sheet here. Click on the formula sheet, this will pop up, and this is the formula sheet that's going to come attached to the final exam. So it has most of the formulas that we've talked about already. So I would maybe recommend printing this off and having this close by to any of the other formulas that we've talked about in class. Definitely make yourself up a formula sheet before taking the final exam, hands down. You need to have all of your common integrals, some of those uncommon integrals, like integral of the logarithm, integral of arctan. Like, it's just nice to have those all collected together. And I want to highlight a couple of these down here at the bottom. So you'll notice that we have like a couple of like the reduction formulas around here, like 22 is the cosine reduction, 24 is the secant reduction. So all of the reduction formulas we've talked about are down here. It also has a couple of these like really awkward square root and a couple of these really awkward a squared, a squared plus u squared or a squared minus u squared things. So number 18 is a shortcut formula for finding out what the arctan thing should be without going through the process of substitution. Okay, so number 18 is helpful if you can complete the square, but everything after completing the square is gross. So you can use 18 after you've completed the square. So what I'm going to do is I'm going to copy this formula down into OneNote. And I'm going to grab the integral that we worked on together. So the one that we got after completing the square, because this is interesting. And for some of you, this might be a helpful thing. So after completing the square, we had, I think, 1 over x minus a half squared plus 7 over 4, right? This was the integral that we had after completing the square. So if I would like to apply formula 18, which is a formula from the formula sheet, I can. They're taking u as the variable portion. Okay, so here we know that u is equal to x minus 1/2. And they're taking a squared to be the constant thing. Now, a squared right now is equal to 7 over 4. That means that a is equal to root 7 over 2. As long as you know these two things, we should be able to plug them into this equality and figure out what this integral is going to be without having to go through the process of substitution. So this integral should come out to be 1 over a. Okay, so 1 over a, 1 over root 7 over 2 times arctan of u over a plus c. So let's see if we can get that to come out okay. Arctan of u, so x minus 1/2 over a root 7 over 2 plus c. Is this right? I feel like I did something incorrectly. Was the root 7 in the numerator or the denominator? It's supposed to be in the numerator. 1 over a. Did I do a wrong? Did a do me wrong? We had the 2, so the 2 canceled. Weird. Is that correct? Okay, why is it 4 over 7? No, it was 7 over 4, right? I'm not going crazy. See, the arctan bit came out okay, but the constant in front of it came out a little bit differently than I thought it would. I think u and a might be switched. I think u and a might be switched. See, u came out, I guess it doesn't really matter. It does. It actually does matter. So because our integral is in terms of u, u is the variable portion. So that's why I was taking u to be like u squared is x minus 1/2 squared, and a squared is 7 over 4. So I'm not sure exactly why this constant bit came out weird. If I find it in the next 3 seconds, I will let you know. But yeah, it seems like the constant term came out a little bit funky. Weird. Anyway, it could also potentially be because there were some other constant terms that we had to like multiply here as well in order to finish this off. But 18 is there, and that I believe that's the right formula. That's the formula that I remember. So this should work if you don't like going through that process of substitution. I just wanted to kind of point that out there. It is a possibility to skip that substitution and use this formula instead. I don't want to dwell on that constant, otherwise my brain is already mush, so I don't want it to be more mush. If I figure it out, I'll let you know. What I would like to do for the next few minutes is just do a quick little recap of sequences. And that way, when we get together on Wednesday, we should be in pretty good shape to talk about maybe the last technique, which is improper integration. I think maybe we'll try to do that on Wednesday. Yeah, so let's just redefine sequences. And I'll give you a couple of theorems that I think are helpful when we're thinking about sequences. I don't want to spend too much time on sequences. You'll spend a lot more time with sequences inside of an analysis course, and you'll really develop a lot of theory in there. But I want you to have a kind of an idea of what sequences kind of look like and how they act. So a sequence is basically just a list of ordered numbers. Okay, we might write it out as a set. So we might write it out as a set of ordered numbers, a sub n, and the n here just represents a natural number. So you can kind of think of it in like the following way. Like let's say we have a rule. Let's say we have a rule that is, I don't know, n over n plus 2. So here's our rule to define the sequence. And what we do, it's kind of like a function where you can kind of substitute numbers into this rule. But the only numbers that you're allowed to sub into this rule are natural numbers. So numbers starting maybe at 0 or 1, and then increasing through the whole numbers. So if we wanted, for example, to start at 0, term 0, we could go 0 over 0 plus 2, and that's 0. A sub 1 would be 1 over 1 plus 2. That would be 1 over 3. Again, we can keep doing this. We can pretty much get whatever term that we want by substituting in some whole number in for n. So that's really the key here, is we're really just kind of thinking about whole numbers for n. And then we could, if we wanted to, write out this sequence as a list of numbers. So our particular an would contain the following numbers. If we wanted to start at 0, the first number would be 0, followed by 1/3, followed by 2 over 4, which is a half, and so on and so on. And this just kind of keeps going, and we can go as far as we want. But really, it doesn't have any kind of end to it. So this is what we started looking at with regards to limits at the very start of our calculus course. And remember, the big question that we asked was, if we have this ordered list of numbers, do these numbers tend towards something? So the big question that we often ask is, are these numbers tending towards something? Okay, so do these numbers tend towards something, or do these numbers get really, really big? Do they get really, really big in the negative direction? So this is kind of the question that we ask when we have a sequence of numbers. And really, like, 3 things could happen. The first thing that could happen is if an tends towards a numerical value, we say that that's the limit of our sequence. So that's one thing that could happen. And then the other two things that could happen is it could be unbounded. It could be unbounded in maybe the positive direction. It could be unbounded maybe in the negative direction. Okay, remember in these particular cases, we would often say that the limit doesn't exist, but often it's a weird mathematical notation. We use the equal sign with that particular infinity. So we could still write something like this. We could still say that the limit, as n gets really, really big of our sequence, we can still write plus or minus infinity. We were allowed to write this to let our reader know that this sequence gets unbounded. But technically, a limit doesn't exist. So that's something that could happen. And there are some other weird cases that can happen too. I don't want to spend too much time talking about the weird cases, but I mean, you could have a sequence that it's not unbounded, so it doesn't get bigger and bigger, and it also doesn't go towards a limit. So it's possible to have this weird third case where neither 1 or 2 apply. So there is a kind of this weird, also see if I can make one up. So usually I think what happens here is maybe if we bounce back and forth between a couple numbers. So think about sine and cosine, for example. These are functions that just kind of keep repeating over and over again, and there's no limit as we think about sine and cosine going off towards positive infinity, right? They kind of keep bouncing back and forth between -1 and +1. So this is kind of like that third case. So if we maybe take, so for example, we take an to be just bouncing back and forth between +1 and -1. Then this sequence doesn't have a limit because the numbers don't tend towards something. They actually keep bouncing back and forth between two different values. Right, so in other words, this sequence that we have of bouncing back and forth between 1 and -1, it's not unbounded. It's always kind of stuck in between 1 and -1. It also doesn't tend towards some number. I mean, maybe one of you wants to argue with me that we could have 2 limits, 1 and -1, but from a calculus perspective, it doesn't really make sense to talk about 2 limits. We want it to be a definitive y value. So it doesn't really make sense to say that this has a limit, and it doesn't make sense that it's not unbounded. We're just kind of stuck in limbo. We're stuck inside of this weird horizontal band. Now, we did talk about the actual definition of a limit in the first part of calculus. If you want that definition, you can go back and take a look at your notes. Essentially, what's happening is, let's say we have a sequence. Okay, a sequence, when we're dealing with an a sub n like this, comes as a set of dots. So we're not thinking about a sequence from a functional kind of perspective. We're thinking about it as just a set of dots inside of the xy plane. Each one of these dots lands on x equals 1, x equals 2, x equals 3, for example, or maybe n equals 1, n equals 2, n equals 3. And then we're kind of looking at, okay, what are the y values that correspond with this set of dots in the n, let's say the ny plane, right? So this is a sub n maybe. And the true definition is kind of taking a look in the long run and seeing if we land inside of a horizontal band. So you can go back, take a look at that definition if you're curious about it. Inside the middle of this horizontal band, we call this capital L. And then if you remember, we had L plus epsilon and L minus epsilon as the other horizontal lines inside of this vertical band. So the idea is if we can kind of crunch this horizontal band down as far as we would like to go, it's possible to say that the sequence tends towards the limit L. So this is the picture that kind of goes along with number 1, right? So we say that an tends towards limit L if I can kind of eventually get stuck inside of this horizontal band. I don't want to do any proofs with that. So maybe let us just write down a few theorems that could potentially be helpful when thinking about sequences. Okay, the first theorem that might be helpful goes like this. So if you happen to know the limit of a function tends towards L, okay, so let's say you know that f of x, I don't know, this means that f of x has a horizontal asymptote. So if you know that f of x has a horizontal asymptote at y is equal to L, and you happen to know that this function and the sequence that we're working with match up at the whole number values for n, then you happen to know what the limit of the sequence is as well. Okay, so in other words, if a sub n looks like a function that you already know about, and you already know about the horizontal asymptote of this function, then you can use your knowledge of limits from calculus 1 to think about sequences that only have one variable n in them. That's what number 1 is saying. So for example, let's say we were looking at, I don't know, this limit. Okay, so maybe I'm curious about the long-term behavior of this sequence ln, so logarithm of n divided by n. What we could do is we could reframe this question in terms of thinking about ln of x divided by x. And that's going to allow us essentially to go into Desmos now, plot this function, and see what happens with this function. So let's do that. I'm going to get that open and running in the background for us. Alrighty. So here is that function in blue. This is the logarithm of x divided by x. Our sequence is going to look very similar to this, It's just going to have like ordered pairs at every integer value of x, essentially. So where does it look like this is going to in the long run? So, if I think about the limit as x gets really, really big, so it pops up and then it starts decreasing. So it looks like we're tending towards 0, right? It looks like my horizontal asymptote should be y is equal to 0. Interesting. Here's a functional example of a function that comes over its horizontal asymptote and then comes back down towards its horizontal asymptote. Interesting. A function can cross its horizontal asymptote. Okay, so we know that that tends towards 0. We just use Desmos for this. If you wanted to prove that algebraically, you could use L'Hopital's rule. Okay, and you should be able to very quickly show that that tends towards 0 by applying derivatives here to this limit. So we just looked at Desmos. That's fine with me. So because this is true, I know that the original limit, just thinking about the integer values, must also tend towards 0 in the long run. Okay, so that's one strategy. If you're working with sequences and you know that sequence looks like a function that you think you can work with, just work with the function. Okay, second helpful thing is the squeeze theorem. So this is just an application of the squeeze theorem. If you know that you can bound your sequence in between some other kinds of sequences, or that's maybe given to you in the question, then it's possible to take a look at the limits of the two bounding sequences. If they tend towards the same value, then the other one has to as well. So this is what we call the squeeze theorem application. And it looks something like this. So basically we have, I don't know, maybe in green, I will put our sequence. And then maybe in red, I'll have an upper sequence. And in red, we'll have a lower sequence as well. So the idea here is that your upper and lower sequence, they are tending towards some y value L. If your green sequence kind of lands in between the upper and lower bounding sequences, and in the long run, that means in the long run, the green sequence should tend towards the same number as B and C. That's kind of the idea of number 2, or at least the visual that goes along with that. Okay, some sequences that we want to work with are going to be called alternating sequences, meaning that they're going to be bouncing back and forth above and below the n-axis, essentially here, the x-axis. So a typical thing to do is to look at the absolute value of these numbers. And if the absolute value of these numbers tends towards 0, then the original sequence should as well. Okay, and usually this is used when your sequence begins with this alternating -1. So we have a factor of a -1 to the power of n. And I'll try to look up and try to get some good examples for us for Wednesday. But yeah, the idea here is if you're kind of bouncing back and forth between some stuff, you can kind of hopefully utilize number 3. Notice that it doesn't work for this sequence. So notice that, you know, if we think about this sequence again, the one where we kind of bounce back and forth between positive ones and negative ones, if we consider the absolute value of this sequence, we just get 1, 1, 1, etc. And if I think about the limit of this sequence, I get the number 1. So why doesn't this sequence satisfy number 3? So is it true that we can use this to argue that the limit of an is also equal to 1? Is that a thing we can do? Well, not really, because the statement in number 3 is very specific about where this limit goes. Okay, so number 3 says if we're alternating signs, like we are in this particular example, and the limit tends towards 0, then and the absolute value limit tends towards 0, then the original limit will tend towards 0 as well. So the idea of the limit tending towards 0 is an important part of the theorem in number 3. That has to happen. And because when we take the absolute values limit and it tends towards 1, we can't apply number 3. So the answer here is no. No, we need the limit to tend towards 0 in order to utilize number 3. Okay, and the last thing that could potentially be helpful here as we start thinking about sequences is if you happen to know the limit of a sequence, then you can find the limit of a brand new sequence by just taking the function. So like this is a composition kind of thing. So if you happen to know where the inside of something goes, then f of that sequence that you've looked at should go towards f of L. And this only works if f is continuous. So this is the kind of composition rule of limits. And we've seen this with functional limits, right? So we were able to kind of move the limit inside of the function, provided the function was continuous. So this is kind of a very similar rule for sequences. So that's really what I wanted to cover for today. This is a little introduction and a couple of helpful concepts. Maybe we'll work through a couple examples of sequences from the textbook, I think, maybe on Wednesday. And then what I really want to start covering is I really want to start thinking about series, which is, or actually, no, we should be able to do improper integration, I think, with just, we might need series. We might need series too. So we're going to go one of two ways on Wednesday, either into improper integration, if I think I can do it with just sequences, or I might have to cover a little bit of series, which is like the thing where we add up all of the stuff, and then do improper integration after that. So it depends on what we need. I think I can do it maybe with just sequences, but we might have to do sums first. So depending on what we need, that's kind of where we're off. So we're kind of just starting off like chapter 11.1 and 11.2 right now, for those of you that are curious about where we are. All right, so I will work on getting that quiz up for you guys. Sorry that it's coming a little bit late. Remember, that's going to be due on Sunday at midnight. Okay. You are welcome, Nathan. No worries. Yeah, thank you very much. Thanks for coming, Amy. Logan, it's great to. Yeah. Thank you. You're welcome, Kieran. Yeah, thanks for being here and doing a thing. I did. I got some shiny fletchlings on community day, even though I was stuck in Kelowna. I only got about 10, but I was able to kind of half catch stuff while doing my line training. So yeah, I was able to get a few, Owen, which is kind of fun. You're welcome, Kate. Have a good rest of your day. Good afternoon. Go take a walk. It looks beautiful outside. Get that walk and get those steps in. Yeah, we can definitely do a trade eventually, Owen, for sure. Are we lucky friends right now?